Our next topic deals with complex ions. Now, complex ions is the third of the three types of ions that we've had to deal with. One dealt with binary ions or binary compounds with only two elements that were ionic. Then we had the polyatomic ions, and then we have this, the complex ions. The complex ions deals with what we call Lewis bases. Now, a quick overview of bases. We know what acids are. We generally know what bases are. They're the opposite of acids. But there are three definitions of acids and bases. Arrhenius is one. Arrhenius acid is one that gives up hydrogens. But Arrhenius base is anything that gives up hydroxides. Example, sodium hydroxide, where this OH comes off. And it's a strong base. This is another strong base. Strontium hydroxide, where both OHs come off of that. This is a weak base, where this is methyl ammonium hydroxide, very weak base, but this OH is what comes off of that. So by definition of Arrhenius, that is giving up the hydroxide. Brunstad-Lowry base, however, is defined as accepting a proton, where the Brunstad-Lowry acid gives up a proton, the base accepts the proton. Remember, acid bases are exactly opposite. So what one does, the other does just the opposite, just probably out of spite. The example here is ammonia. Ammonia, the Lewis dot structure, has a pair of electron dots that are not shared, so that is going to attract a proton usually in the form of a hydrogen ion. Create what we call ammonium ion. But this, because of that attraction, that allows this ion to take place. A Lewis base, however, is exactly the opposite of Lewis acid. A Lewis acid accepts electron pair, where Lewis base gives up an electron pair. This is the same Lewis who came up with the Lewis dot structure. So he's all about electron pairs. And the examples that I'm giving here are the ones that are used in the problems that you're about to have. Again, ammonia can be defined in terms of that, in that it will, when I say gives up electron pair, that actually will share electron pair with an atom that is lacking two electrons. We dealt with compounds like that when we did Lewis dot structures, when we had sulfuric acid and you had sulfur that had given up too many electrons, didn't need any more electrons, so it will share an entire pair with another atom. It happens a decent amount of time. Cyanide, like cyanide gas is HCN. Well, this is that. The cyanide gas will have an electron pair that's given off here, and the whole thing is a negatively charged particle. Hydroxide, which you're pretty familiar with, will have a negative charge, -1 charge, and this electron pair will be shared or given up, depending upon what is required. This is called thiocyanate. Thiosulfate. And then basically it is a sulfate ion in which one of the oxygens has been replaced with a sulfur. That's what the thio, T-H-I-O prefix comes from, means sulfur. So thiosulfate is a -2 charge and has electron pair. It is also very willing to give up. As you can see, it's just loaded with electron pairs out there. And water is indeed a Lewis base, as well as a Lewis acid for that matter, just like ammonia. But it will give up an electron pair or accept a proton to create the hydronium ion that we talk about sometimes. All right, so how does this work? Well, I really hope that you've had a chance to look at the two videos before we get into this. In fact, if you haven't, you probably should stop now and look at Professor Dave. He has a really good explanation. But the one that's pretty dynamic is the one in which you actually see what these things look like and how they change the way they do. I'm going to show you the chemical formula for the change, but you really should take a look at it. I had a professor that I worked under in organic chemistry at Ball State. We were designing compounds that we hoped would kill cancer cells, and they did indeed kill cancer cells, but the problem was they also killed all the cells around it, which is kind of self-defeating. So, but it was kind of exciting stuff. And this guy was a little down about not getting his stuff to work properly. So he went off to the University of North Carolina and became a specialist in complex ions. And he had some of those gorgeous compounds that you've ever seen. It's really kind of cool. If you like colors, you like this. And there's a lot of uses for complex ions. But getting back to this, an example of a reaction which we can see this taking place, take silver chloride, which is an incredibly insoluble salt, and you add to this 2 ammonias. Now, this is going to be aqueous, so technically it's ammonium hydroxide, but it's the ammonia that is the active part of this. This is going to be attaching to the silver ion. This is going to kick out the chlorine and attach itself to the silver and create a positive complex ion. We call compounds like these ligands. So all these Lewis bases I showed you here, those are all ligands. They attach themselves to generally insoluble compounds and make them extremely soluble, very highly, unbelievably soluble, just by their attachment because of all these electrons around there that allows them to interact with other atoms around. Where the hydration rate for this, when I say hydration rate, I mean the ability of water to break this apart is almost impossible. But when you get these things to attach to it, they go, oh, we like water, we'll form all kinds of bonds that you couldn't form before, and so this becomes, boom, extremely soluble. So what you see happening here is that this is basically a single displacement reaction, but instead of one of these things going there, both of them go in there. And so you get silver and then 2 ammonias, and that's going to create a positive charge. Why a positive charge? Because these things are neutral. Silver is a positive ion, and chlorine is a negative ion. Silver is one of those weird transition metals that only has 1 charge. In fact, if you see your glossy periodic chart, you'll see the charge is on there, and there's only a 1 for that. It's an exception. It's not, there's some exceptions, not a whole lot, but there's some. Silver's one of them. And so this becomes, like I said, extremely aqueous, and it kicks out that chloride. And so that chlorine now becomes what we call a spectator ion. I believe Professor Dave used that very term. This is, the result, and it changes the color of everything dynamically. So, generally then, we ignore the chlorine in these reactions. And so when I ask you to write the formation reaction, of a complex ion like this one, you won't include the chloride in there. You'll just say silver ions, aqueous, plus 2 ammonia, aqueous, forms the complex ion AgNH3 2 positive, aqueous. Okay, and so, and this, by the way, technically is a double arrow reaction now, because it will go back and forth, but not really a whole lot. Really, this goes mainly to the right, a little bit back to the left, but mainly to the right. But we put a double arrow in there anyway. And so we call this the resulting analysis, if you will, of equilibrium KF. And because they're all aqueous, they will be included in this. And so it's, again, products over reactants, Ag, NH3, 2, positive, concentration, over the concentration of Ag positive, times the concentration of NH3, and that will indeed be squared. And there is a value for this, and I'm hoping I wrote it down. Yes, it is 1.7 times 10 to the 7th. Not negative 7 like all the others we had up to this point, positive 7. And this tells you, according to equilibrium ideas, that when you have your products much, much greater than reactants, you're going to get a gigantic number here. And so this is going, like I said, basically to the right, or way to the right. Although this isn't that big. There's some with the 18s and 20s all the way up there. Now, the reverse reaction then is what they use for calculating solubilities. Now, we're not going to get into that. I just wanted to give you an idea of what this is all about and how they calculate these things. But if you were to take your college level Chem 2, they'll get into this. I don't think it's necessary because we never really deal with it. But I think it's just some cool stuff to look at. But you should at least get a little foundation for how they're going to approach this when they teach you to this at the university level. The reverse reaction is called a dissociation reaction. And like I said, this is the material or the ideas or concepts they use in calculating how much actually is left in a reaction when it runs. All this, what we call quantitative analysis stuff, which I ate up in college, but you don't really need to worry about it right now. But at least understand that it does exist. And this just will be the exact opposite. You're going to start off with your complex ion, your Ag NH3 2 positive aqueous, and you're going to break that down. Again, double arrow. It's going to give you Ag positive aqueous plus 2 NH3 aqueous. So you're like, well, wait a minute, Campbell, that's exactly the same thing on reverse. And I would say, ooh, you're so perceptive. That's very good of you to understand that. Which means then that the Kd for this, K of dissociation, is going to be the reciprocal of what you have. In other words, this is going to be the concentration of Ag positive times the concentration of NH3 squared over the concentration of Ag NH3 2. And that's going to be equal to 1 over the Kf, which I said is 1.7 times 10 to the 7th. Now, when you do these problems, that's going to give you the step to the final answer. I'm not going to want to look at this. I want to see the resulting value of this, which is 5.88 times 10 to the negative 8th. Which means, again, it's going mainly to the left, which is what we expect, because when it was reversed, it was going mainly to the right. So mathematically, this makes sense. But like I said, when you start getting the quad form and large numbers, and the quad form doesn't work very well, but it works really well for a smaller number, so they like to use this instead. And rightly so. At any rate, all you're going to be asked to do is to give the Kf and Kd, well, you need the reactions, and then the Kf and Kd expression for it, and the numerical values. Okay, so your practice problems are given to you in the Google Doc sheet. Have fun.